We had just discussed some time ago about a control system, that is voltage regulator, how DC output voltage can be maintained constant by comparing the output voltage with the reference and making a series pass transistor have the drop across it controlled by a comparator output. Similarly, we are going to now discuss what is called AC voltage regulator, or I would call it as automatic gain control system. It is popularly called automatic volume control system, AGC AVC, or in another application it is also termed as amplitude stabilization of oscillators. The output amplitude of the oscillators maintained constant at a certain value. Here input comes from an external source, and therefore output is maintained constant. Here input is actually generated within itself in an oscillator, but its amplitude has to be maintained constant. So that is the difference between these two, but both of these require similar type of gain control system so that output remains constant. So such an AC stabilization scheme is what is going to be talked about. So before we go to this sort of theory proper, why it comes into picture in multiplier? Multiplier we know is nothing but an amplifier whose gain can be controlled. So basically a multiplier is the ideal block into which this control system can be incorporated. So as an application of multiplier, we can use these systems. So basically I would now take a multiplier itself as a block to which we will now apply a control system. What is it? I have Vi applied to Vx, and this is the control voltage. If I ask you to maintain the output constant, you will ask me at what value. I will say at a certain value, 5 volts peak or 10 volts peak. So this is a sine wave. It is understood that this has to be a sine wave. So this or a single frequency or a narrow band frequency, right, output. So this is Vp I sine omega t. This is the input. Output therefore is Vc by 10 times Vp I sine omega t. So what is asked is that this should remain a constant at a certain value. Let us say this is going to be Vr. So how do we maintain this constant? Vpi, if it decreases, Vc should increase, so that Vpi into Vc remains a constant. So that means if I ask you to maintain this constant, for a certain Vpi you will apply a certain Vc, so that Vpi into Vc by 10 becomes equal to some Vrp, let us call it. So this is the automatic gain control scheme or automatic volume control scheme. What it needs is an amplifier whose gain is controlled by means of a voltage or current. And these amplifiers should be working at a certain single frequency or a narrow band frequency. Now where do we really apply these AGC AVC schemes? These are all applied to receivers. At the receiving end you receive the carrier, and this may be amplified by an RF amplifier and applied to a mixer. In mixer it is converted to IF, and this IF is further processed, amplified, and then detected. The modulated frequency is detected. So the entire chain of receiver where this information gets amplified, or the sensitivity of the receiver is sort of primarily to do with gain of IF as well as RF. So that the sensitivity is packed. So if I have the signal that is being received very large, then the output will have a large magnitude of output, and my audio stage may get overloaded, distortion may occur. If the input is very small, output will be very small, and I might not get any detected output. So, this kind of thing occurs normally because the received signal keeps on fading due to atmospheric conditions. Okay. Attenuation keeps on fluctuating at every moment. So, this kind of variation, this fading, at sometimes the received signal is large, at sometimes the received signal is small. Okay. This kind of thing, when it happens particularly, you want your automatic gain control system to function, so that the output of the IF is fairly constant. So, that at this constant value the distortion is not there, and also there is sufficient signal output, okay, so that you can hear this. So, this is absolutely necessary in almost all receivers, television or audio, that is radio receivers. So, you will see that the gain of IF stage and RF stage as well as mixer is controlled by some current or voltage, and that controlling current or voltage is derived from the detector DC. The DC information that is outputted at the detector is directly dependent upon the amplitude of the IF received. Okay. So, how do we receive this DC information? We have to convert the AC into DC. So, for that we have to have a rectifier diode arrangement. So, we will discuss that also. Essentially, there are 2 points. This is normally applied to an amplifier which is working at a single frequency or a narrow band of frequencies. That is why we can take the signal as sine wave, okay, and output is going to be sine wave, and this is going to be rectified and filtered, okay, in order to derive a DC which is dependent upon the peak value of the signal, and this DC information is used to control the gain of the amplifier. So, if this is increasing, input is increasing, gain is decreased. If the input is decreasing, gain is increased, so as to keep the output constant. So, this principle is the principle on which this is operating. Now, what is the range in which this AGC system will work? Let us see. Vc at most can be equal to 10 volts. So, when Vc is 10 volts, Vpi has to be equal to Vrp. So, when Vc at most becomes equal to 10 volts, okay, Vpi has to be equal to Vrp, or when Vpi is equal to Vrp, Vc will become equal to 10 volts. If Vpi, okay, is less than let us say Vrp, let us say Vpi is less than Vrp, Vc has to be greater than 10 volts, which is not possible. That means, Vpi cannot take any value which is less than Vrp for this structure. So, Vpi minimum is equal to Vrp. That is the range in which this system will work. That is the maximum gain you can give from your amplifier. So, the maximum gain times the minimum voltage should be equal to whatever value you want. That is number 1. Then, when Vc is equal to Vc minimum possible. Now, Vc minimum can be very nearly 0. Okay. Vpi can be any large value, right. So, any large value greater than Vrp it could be, right. So, for all those large values Vc can take on the minimum value. So, there is no problem. So, as far as this AGC system is concerned, it is going to work for a variation of voltage starting from Vrp up to very large values of the signal. Okay. This because this is basically an attenuator, not really an amplifier. So, this particular thing, this Vc minimum is going to be fixed by what will be the order of minimum voltage that is necessary for the multiplier, at which multiplier will satisfactorily multiply and act. This is normally about 10 times the offset voltage of any of the op amps and things like that, that are used in the multiplier. Okay. So, that there is certainty about the value that you are considering here. So, basically therefore, you will see that if I apply V I versus V naught, V I peak versus V P I versus V naught. Okay. V naught is this, V naught peak. Okay. It will be just that this will get stuck at 10 volts, okay, when V P I is low, because it is trying its best to give the maximum gain for it. So, it is not working at that point of time. So, what will be the gain? Gain is going to be 1. That means, it is going to follow like this. If they are of the same scale, there will be 45-degree line up to the point when this becomes equal to 10 volts. Okay. That is, this also can become equal to 10 volts now, right. So, up to let us say VPR, VRP or 10 volts, whichever is going to be the lower one, right. So, we say that we want it to be adjusted to 10 volts, then, right. Thereafter, it is going to get controlled. VPI minimum equal to VRP, up to that point is going to be, then it will be controlled. If VRP is 10 volts, this will be limited to 10 volts. Okay. So, but then VOP also cannot be greater than 10 volts, because this is a multiplier, right. So, you have to make VRP less than 10 volts. So, let us say I am adjusting this to be 5 volts. Okay. So, this limit is at 5 volts. Okay. So, the moment VOP becomes equal to 5 volts, it will start controlling. Then I should not apply VPI greater than 10 volts for this. So, up to that point it will work, the AGC will work. So, this is the characteristic. This is the characteristics within which it is simply acting as an amplifier without any control. After this, control takes over and output will remain constant. Okay. So, every AGC system will have a dynamic range within which it is satisfactorily functioning, right. So, this is the dynamic range from this value up to 10 volts. Okay. So, if I decide that VRP shall be 1 volt, then this is it. You will see that it will be constant. This is the characteristic of the AGC system. If it is to be 0.5 volts, you can see that as I restrict the value of this to lower values, okay, the AGC dynamic range keeps increasing. As I keep on increasing it, let us say I have it at 10 volts, there is no range at all for the AGC system, because my multiplier will stop functioning beyond 10 volts. Okay. So, this is how you can arrive at the dynamic range of such systems. Now, how to implement this system? First, let us see how this information can be converted into a DC. So, this information can be converted into a DC simply by connecting a, let us say, rectifier here. So, if this is connected to a half wave rectifier here, right, the output of this will be going up to the peak value. This we have learnt in our earlier course itself. Let us say after generating this rectified waveform, I want to filter this. How can I do that? That can be done by putting a low pass filter. This is the arrangement of the low pass filter. It is assumed that this low pass filter is not loading this particular resistance R. Okay. This resistance R is the one which uniquely fixes up the current in this diode, so that this is not loading it. Okay. So, we can have a low pass filter like this. Now, so what will be the low pass filter now determining? It will take the average of this. So, if this peak is given as V naught P as specified here, this will give us V naught P divided by pi. This we had evaluated earlier also in the half wave rectifier. This average DC voltage here, if I put a sufficiently large value of capacitor, how do I fix up the RC time constant? This RL into CL should be much greater than the time period T. Okay. Time period T is the time period of this half wave rectified waveform. Okay. This we know. In such a situation, the DC output voltage here is going to be V naught P by pi, and this DC voltage can be used, assuming that the diode is an ideal diode. Okay. We have got this much information, that the DC voltage is V naught P by pi. Let us see, if this increases, okay, this voltage is going to increase. So, this information gives straight away the fact that I have to decrease the gain. So, I use this to control. I compare this with another voltage called, let us say, V reference, and this voltage I am going to apply to the controller here. So, when this voltage goes above V reference, let us see how to put the polarity. I am putting the polarity here in this manner, because I know that when this voltage increases, I want this voltage to decrease. If I put plus minus here, when this voltage increases, this voltage will increase. So, minus plus, that is what is called negative feedback. So, when this voltage increases above V reference, this voltage will start decreasing. So, it will start decreasing and it will control the control voltage here, control voltage here, such that the gain reduces. So, let us say V naught increases above what we want. What we want is this average should be same as V reference. If it is more, then this will go towards negative saturation. That means, it will become less positive. If it becomes less positive, this decreases, because Vc is decreasing. When this decreases, this difference, okay, becomes smaller now. Ultimately, this should decrease until this voltage becomes equal to this voltage, and that voltage will remain constant there. As long as this is remaining constant, this will remain constant. Right. So, this is the basis of negative feedback AGC. Okay. So, we have now built a system which is called automatic gain control or automatic volume control. This rectifier filter combination will measure the peak value voltage, okay, and compare it with V reference and have the control voltage controlled in such a manner that the gain is decreased if the amplitude is increasing and gain is increased if the amplitude is decreasing. So, basis of such automatic gain control and automatic volume control, okay, the rectifier filter combination is one part that is necessary there. Normally, if the voltage that is inputted to such system in communication area, this voltage is very small, then V gamma of this diode will hinder this rectification properly. Right. So, for that purpose we can use what is called a precision rectifier here. So, I will discuss how we can replace the diode resistor combination here by what is called as a precision rectifier, which can rectify very small voltages as half wave, okay, even if the peak value of the voltage is less than V gamma cut in voltage of the diode. We had seen how this AGC system involves basically an amplifier with gain control, rectifier with filter and voltage reference. So, these are the three basic components of any AGC or AVC system. If it is an amplitude stabilization of oscillator, it becomes oscillator, okay, with gain control there, and then rectifier with filter and voltage reference. Now, the rectifier, we would like to discuss a circuit for precision rectification using op amps. We had seen this phenomenon in the removal of distortion, crossover distortion in class B amplifiers using op amps. Same thing, we can use same principle we can use of feedback. I have a resistance here which will convert the voltage into current, okay. Negative feedback therefore is going to be made available through a resistance where the diode conducts. So, the diode conducts based on current, not based on voltage. Okay. If this voltage is positive and this current is positive, that current has to go into the diode, that is irrespective of the value of the current. So, the diode is going to conduct even if the current is pretty low. So, as long as Vi is greater than 0, this current is positive and the diode automatically conducts. Why? Let us try to understand. If the diode does not conduct, okay, then this is an open circuit. If this is an open circuit, this voltage will directly appear here and this voltage will try to go to negative saturation. That means, this diode will be forced to conduct, okay, because this voltage will go towards negative value. So, if the op amp is such that op amp does not get negative feedback, then the open loop causes this voltage to appear here, even if it is a small positive value microvolts, this will try to go to negative saturation and the diode will jump to V gamma. So, this is what is happening. This op amp will try to make the diode conduct even if the voltage is a small positive. So, if therefore, this is small positive and this is R and this is R, this is going on becoming positive like this, say half wave. This half wave is exactly reproduced here, but is going to be inverted, because this current will flow like this will flow like this, and this potential being 0 virtual ground, okay, there is an inversion here. So, if this is Vp, this is minus Vp for a voltage which is taken here. Therefore, you should not take the voltage at the output of the op amp, because what will it show us? It will show us a jump initially at the 0 crossover, because this is going towards minus saturation. As soon as the V gamma is reached, this diode is going to conduct, and thereafter it will show this half of the waveform. So, this is minus V gamma and this is minus V gamma plus minus V gamma minus Vp. So, that this particular point is going to have in addition to this voltage, okay, the diode voltage here, which is minus V gamma. So, this is not what you should take. In fact, if Vp is let us say 1 millivolt, okay, this V gamma is about 700 millivolts. So, actually you will not see this peak at all, it will look almost like a square wave here, whereas it will be a nice rectified half wave here 1 millivolt with 1 millivolt peak. So, this is what is called a precision rectifier. This is not over, because if this voltage now goes positive, this is understood, it is going to half wave rectifier. When it goes negative, what happens? When it goes negative, we want this voltage to be at 0. When it goes negative, no diode is there, op amp is not conducting, op amp is not having negative feedback, and therefore, this negative voltage will directly appear here, and this will go to positive saturation. So, this voltage will appear here, and this negative voltage appearing here will make it look like a full wave rectified waveform. But then I cannot draw any current from it, because the moment I draw a current here R L, okay, that will get attenuated, because op amp is not coming into picture. This resistance in series with R L is going to cause an attenuation. That means, this peak amplitude will keep varying depending upon R L. Whereas, earlier when this was going positive, this was negative, the R L did not matter at all, because it is the op amp which was giving the current to the load. Okay. So, current was not being taken by the load resistance from input. Okay. It was the op amp which was delivering the current to the load. Now, op amp does not come into picture. So, the peak value of this will keep changing with respect to R L. So, how to make it constant at 0? The only way is to connect a diode in the reverse direction. Okay. So, what will this diode will now conduct and maintain this voltage at 0 whenever this goes negative. So, a half wave rectifier for a precision diode requires 2 diodes with op amp, one to maintain the negative half of the waveform when this is going positive, other to maintain during the other cycle the voltage equal to 0. So, this will maintain the virtual ground, that is negative feedback will come into picture even when the voltage is going negative, and therefore, the op amp will still function now, but this is the waveform. This is the output waveform at the op amp. The op amp is conducting, okay, on both the cycles, that is necessary, so that the negative feedback is there. Only when it is going positive, the output is coming as negative at this point. So, this is the point at which output is going to be taken. So, please remember that both diodes are necessary. If it is positive half you want to select, you will invert the diode here and put the other diode in the other direction here. So, this is the circuit for a half wave rectifier, precision rectifier. Right. You can use this therefore, as your rectifier for the circuit that we have mentioned. Put a low pass filter here. Okay. After this you put a low pass filter R L, C L, and then put the comparator. Please see here that now I have obtained the negative voltage as the peak, right. So, it will be, this voltage will be minus V p divided by pi. So, I can compare it with the again V reference which is negative, because this voltage will always be negative. So, I have to have a V reference which is negative and appropriately apply the feedback here, so that this system now functions satisfactorily. Is it clear? So, I will leave it as an exercise for you to find out what should be the polarity here, should it be negative or positive, so that the entire feedback system becomes negative feedback system. How do you find out that? Assume that this amplitude is growing, this becomes more negative than this, okay. It is being compared with the negative voltage. If it becomes more negative, okay, what should happen to this voltage, okay, such that the gain is reduced. Now, again here the voltage can be negative or positive. For both negative as well as positive, this will work as a voltage controlled amplifier, but one case there is a phase shift of 180 degree, in another case there is no phase shift, that is the only difference. As far as phase shift is concerned, for amplitude it does not matter at all. So, the phase shift of this is of no consequence for the amplitude here. Okay. But if you decide that this will work for negative only, then correspondingly you have to select the polarity here. Okay. If you decide that this shall work for positive only, then correspondingly the polarity will be different for negative feedback. Okay. So, this is some point that you should bear in mind. Let me do it only for one polarity now. Let us assume that this is working only for positive, in which case this becomes more negative than this reference, this is this minus V reference. This is more negative than this, and I am putting it here positive, let us put. This becomes more negative, that means this is going to become more negative, or it will go to negative saturation. Okay. It is becoming more negative, but I am assuming that it is working for positive voltage, that means it becomes less positive, that means gain reduces. So, this is negative feedback here. If I am assuming that it is working for negative voltage, then the polarity will be opposite. Is this clear? So, this arrangement, you can see that this capacitor has to be very huge, because RC should be much greater than T. So, you can make it work actually by putting here negative and positive, and assuming that this is working only for negative voltage here, right. So, then I can put this capacitor as a feedback capacitor. This is called Miller effect, that also I have discussed earlier. So, this capacitor appear as a huge capacitor at this input. That is possible only if this is negative, because this has to give negative feedback. Okay. So, this controller now becomes this way. Another variation of this is, instead of using minus V reference, okay, and connecting it here, I can remove this and connect it here and make this plus V reference, and this also RL. So, if now this is giving you a current, I mean taking a current which is minus Vp by pi divided by R, then I have to pump in the same current, so that this voltage is maintained at 0. Okay. This is called current comparator, the other one is called voltage comparator. Here the voltages are compared, here the two currents are compared, so that this voltage is maintained at 0. Okay. Both of these things work satisfactorily without any problem, but it is more common to use this kind of thing. You can see that this uses what is called an integrator here, and this according to the control system people is called integral control system. Integral control system. So, the error, steady state error is supposed to be 0 in an integral control system, even though it is very slow. Okay. It is a slow control system, but steady state error is 0. That means, what is the amplitude of stabilization? Vp by pi becomes equal to V reference. So, Vp is equal to pi into V reference. I can therefore vary V reference and adjust it to any voltage I want, okay, output. So, this control system is very popular in most of the so called proportional integral control system. It is called proportional integral differential. Instead of integrator I use a differentiator, it is called differential, but normally these are all used only for improving the transient response of this thing. It is basically proportional, because an amplifier is used for comparing. Integral, okay, if a capacitor is used. Differentiate, okay, if a differentiator is used. As normal control system is called PID controller. This is called integral control system. So, take example 26, design an AGC AVC system using a precision multiplier to keep the output peak amplitude at 100 millivolts. The fact that I have chosen 100 millivolts immediately tells us that we must necessarily use a precision rectifier. Okay? That is why I have chosen this example. So, straight away let us put the precision rectifier. I am going to take a sort of different configuration here. Instead of the negative going thing, I will take the positive going thing. So, if you connect this kind of structure R, when you have a waveform like this going here, going up to Vp, this particular thing is going to conduct only when this goes negative. So, this will be positive and that will be negative. So, output here if you take, this will be going positive, 0 positive, 0 positive. So, this is the kind of output you get out of this. And if I therefore put a low pass filter here, you will get Vp by pi here. So, I now compare this again with, let us say, I will put this and put minus V reference here and R L here. The CL is going to be put now between this and this shall be negative. I want to prove that this shall work now for a certain polarity of voltage as negative feedback. Let us consider this. So, this is the Vi, which is Vp I sin omega t. So, here we have Vc Vp I sin omega t divided by 10 as the output. Okay. The Vc can be positive or negative. We want to see for which one it is negative feedback. Okay. That is all, because all the other things are frozen here. So, we have now the choice to see whether it is positive feedback or negative feedback for positive or negative voltage. Let us see. So, this output is what is coming here, this is rectified and this is what is coming here. It is compared with this, and when this current is the same as this current, okay, there is steady state reach. That means V reference, okay, into V reference is equal to Vp by pi if these resistors are the same. Okay. So, in our case we want this peak to be equal to 100 millivolts. So, Vp is equal to 100 millivolts. So, that is equal to pi into V reference. So, we have V reference equal to 100 millivolts divided by pi millivolt. How much? 31.8. So, that is the V reference that you have to connect here in order to make the peak voltage equal to 100 millivolts constant. Okay. Now, if this becomes more than this 31.8, then this is going more positive. When this goes more positive, okay, this current is going to be injected here more into the capacitor, and this will go more negative. Okay. This will go more negative. That means, let us assume that this is positive. This becomes less positive, and therefore, the gain reduces. So, this is negative feedback for Vc which is positive. So, I have to prevent it from ever going negative. This should not go negative. So, what should I do? And that is done by introducing a diode like this. What will it do? The moment this voltage tries to go to negative, this diode will conduct and this will make it climb down to 0. So, this is climbed down to 0. Okay. So, this is the technique of sort of preventing it from going negative and causing us problem, right. Now, if it is climbed down to 0 ideally, then there is some problem, there is no gain. Okay. So, there is no gain at all here, that means output will not come at the output of the multiplier. So, we do not want it to be stuck down at that particular situation. So, now is that the problem? To start with, let us say this particular thing input is not applied or input is very low. Okay. At that time there is nothing coming here, okay. This is 0, only minus V reference is applied to this. So, minus V reference is applied to minus. So, this will go to positive saturation. Okay. If that is plus 10 volts, let us say, then this has the highest gain at that time. So, output will come. Okay. So, there is no question of this ever going to negative here as long as this is applied. So, this even accidental situation of this going to negative saturation is prevented by this, that is all. But to start with, this has good starting point because okay, at the starting point this amplifier is giving the highest gain. That could be when the input is not there or input is too low. Okay. Both the situations it should be kept in waiting, okay, for the input to come. Okay. So, for every control circuit there is what is called starting point to be verified, whether it is starting properly or not. Okay. So, when the control circuit is not functioning, there should be proper starting voltage applied here. So, in that situation this proper starting voltage for this circuit is plus 10 volts. Okay. So, supply voltage is plus minus 10 volts, let us say. So, this has gone to that plus 10 volts and maintain the highest gain, and then output appears, that is compared, and this gain is reduced. Okay. So, this whole circuit is going to satisfactorily function, and all these additional components are necessary. In fact, if these two resistances are different, then what you have to do is V reference, okay, divided by, let us say R2 we will put it, and this is R1. So, V reference by R2 should be equal to Vp by pi divided by R1, okay, with of course minus sign there. Okay. So, minus V reference divided by R2 plus Vp by pi divided by R1 is equal to 0. So, this is the current equation. In general, therefore, this could be made different, R2 can be made different from R1. Okay. That is why this equation is what is important. So, please remember that this time constant has to be pretty huge in this case, otherwise this whole loop may go into oscillation. There is one possibility. So, that this time constant is the one which is made dominant pole in this whole control circuit. Like for the operational amplifier we have fixed up a dominant pole. If this capacitance and resistance time constant is too small and it becomes comparable with other time constants, this whole system may become a third order system and it may go into oscillation. What does it mean? This Vc is not going to be maintained a constant DC, this itself will change at a certain frequency which is called the natural frequency of this whole system. Okay. So, if you find an oscillation here, it is simply because you have chosen, okay, too low a value of capacitor. Okay. So, that kind of frequency instability can occur in this control system also. Okay. This has nothing to do with positive feedback, this has been made negative feedback. Under negative feedback, okay, this whole system may become, okay, a third order system, that has to be prevented. If it becomes a third order system and the phase shift of this entire thing, okay, becomes let us say 180 degrees, when the magnitude of the loop gain is still greater than 1, it is becoming unstable, and this oscillates at the natural frequency of this system. Okay. So, instead of getting AGC, you will get an amplitude modulated output, because there is a carrier here, okay, and that amplitude modulation frequency corresponds to the natural frequency of the system. If you find that, then you must change the value to higher value capacitor. Okay. This is another important point in the design of such systems. Now, as far as oscillator is concerned, this can form part of the oscillator system like this. For example, a Wien bridge oscillator. So, instead of using a sort of resistive feedback, I can put a multiplier in the negative feedback, because its feedback factor is always less than 1. Okay. So, the multiplier is put in the feedback path of the sort of non-inverting amplifier. Then what will be the gain? This actually is Vc, and this is Vc by 10 into V naught. Okay. So, beta factor is nothing but Vc by 10, or gain of this amplifier is 10 by Vc. So, by controlling Vc, I can control the gain. Okay. So, this particular thing therefore can be used with a Wien bridge oscillator like this, R, C, and then positive feedback. So, it is supposed to oscillate at omega equal to 1 over RC. So, this particular thing has omega equal to 1 over RC and gain is equal to 10 over Vc, because beta is Vc over 10, and therefore, initially the gain should be such that it is able to oscillate. So, we have to fix Vc such that the gain is greater than, let us say 3, that is needed for this. So, Vc should be such that the gain is greater than 3, okay, or Vc should be in fact less than 3.33. Right. So, if Vc is kept less than 3.33, it will start oscillating, right. Then at the required amplitude of oscillation, Vc will be exactly equal to 3.33. That is what such a system will control. In fact, if you just therefore apply this output to this kind of rectifier and the control voltage here, this is what is going to be happening for the oscillator also. So, you can also control the amplitude of oscillation of oscillator in this manner. The only difference is here external input is given, here the input is generated from within itself. For you to assure that input is generated, you must have the gain of this, okay, greater than 3. Okay. So, the amplitude is growing. Then the control voltage will be exactly equal to 3.33, okay, at the required amplitude of oscillation, whatever it be, if you put exactly similar system in this case. Okay. So, as far as amplitude stabilization of oscillator is concerned, it is just like AGC, only thing is gain need not vary by a wide margin here. You can see it should be just greater than 3, or this Vc should be just less than 3.33. So, it can be initially at 3.3, okay, and change to 3.33 at the required amplitude of oscillation. So, the gain need not vary widely in this case. So, you need not use such sophisticated precision rectifier and you need not use a precision multiplier for this purpose. You can just use an amplifier whose gain is controlled by a FET. Okay. So, because the gain variation is very low, 3.3 to 3.33, Whereas, in the case of an AGC system, gain has to vary from a low value to a high value, okay, because we do not know how much the signal varies. So, these are the differences in design of such AGC systems.